he's a third year student at his institution. So these are the participants this year. Actually, we have a better pool than last time, because last time we had 8 students, like after the selection process, but now we have 15, so it's better, I think. Okay. Let me share the screen of the whiteboard. I'm trying to pull it up. Just give me a moment. Okay, great. I believe all of you can see this, right? See this window?
Yeah.
Yes.
Oh, it's still lagging a little bit. Actually, I should turn off the invitation. Okay. So in this course, we already know that we are going to learn a lot about differential geometry. But before going into differential geometry, we should learn a little bit of classical mechanics first, because it's going to be really important in GR. Because the concept of GR, like that equivalence principle and that sort of thing, it comes from basically the idea of mechanics in non-inertial frames. So actually, we need to know something at least something about classical mechanics. So it's going to be a review for many of you, but I think it's worth it. So first of all, I want to say something about like how to study physics. Some of you already have like your terminal degree, so you don't need to know that. But other like those are doing their Bachelor of Science, they need it. So point is, physics is not a stamp collection. Like it's not about collecting data. So when you say like, okay, space is curved and that like this kind of thing happens in event horizon, so it doesn't mean anything unless you know the detail about it. So I'd like to compare with a soccer game. So what would it feel like if like someone told you the score earlier, like the result of the game, and you do not see, like do not watch the game by yourself? I think you don't feel that good to get the score, right? To know the score only. You can compare it to a movie or a novel. Like for novel, like consider any fantasy novel like that you have read. Probably all of you know the Harry Potter series, right? I can assume that.
Yeah.
I think all of you already have read it, and okay, I can use this thing as a reference. So how does it feel like if just someone tells you that, okay, like finally the Voldemort dies and story ends? So how does it feel like? Is it that much like interesting or satisfying, just like the reading the story itself? It's not. So the end result is not that important. Important is the journey. So when you have the result ahead of your time, like we know this kind of thing happens like around the event horizon and that kind of thing, it doesn't feel that good. So that satisfying feeling, it'll happen throughout this journey. That's the important. So that's why we need to learn the mathematics and need to know the connection between physics and the math. So even sometimes it may be cumbersome, it may be overwhelming, but it worth trying. That's what I want to say. So let's get started. I have a list of the topic I'm going to cover today. So basically, we are going to talk about three things in general. One is Newton's laws and its prerequisite mathematics. And then oscillations. We'll encounter a nice differential equation and we need to know the strategy to solve it. And then mechanics in nonlinear shell frame. Mechanics in nonlinear shell frames. So these three things we are going to cover today. So let's start with the measurement in physics, like how we measure our environment or nature, or what do we mean by like some quantity, like the distance is this. So in point of view of physics, we start with setting up a coordinate. So coordinate is a really important concept, but remember, setting up a coordinate, it's a mathematical artifact. It's not physics. So we need to formulate our physics in terms of mathematics. That's why we need to set up our coordinate. But even if we do not set up our coordinate, the physics is there, right? So like consider a point P. We can parameterize our space, like say this is our x coordinate, this is our y coordinate, and attach a coordinate to this point P. But even without the coordinate, this point P is that point, like that very point P. So physics is unchanged, like the choice of coordinates. So that's going to be a really important concept in GR. So whatever coordinate system you choose, even if you do not choose a coordinate system, doesn't matter. Physics is there, and the physics is going to be the same. So how do you measure things? So let's say we are going to measure a length of a stick. So first we choose a coordinate. That means choosing a coordinate means we parameterize, like attach some numbers like 1, 2, 3 along its length. So the unit of this thing, we usually like say that this coordinate and that coordinate, like we know how much that one is, how much that one measures by the unit of it. So say meters. So there is a definition of 1 meter, and we know how much 1 meter is. Now, when you have your 1 meter, then you can say this is my 1 meter, 2 meter, 3 meter. So you put some numbers associated with each of the point along its length. So in the sense, we have parameterized the stick. Do you get it? Is there any question?
No.
Okay. So what happens when we go to a different coordinate system? That means we reparameterize the length. So say that we have a different system, like in US here, people use foot. So say like 1 meter is around like how much? 1 meter is 39 inches, right? So a little bit more than 4. So say this is 1 feet. Actually, it's the drawing is very not to the scale. It's very wrong. So now you have attached a different number along its length, right? But still, it's a parameterization, and it's a well-defined parameterization starting from this point to that point. And still, you can like reach every point on this stick by just saying its associated number. And Also, you have to mention which coordinate you have chosen. Like, are you using feet or are you using meters? So these are your coordinates, right? It's a one-dimensional coordinate, but setting up a coordinate is basically assigning some numbers to a physical thing. Is that clear enough? I think it's better to interact. Like otherwise, I'm not sure. Like someone is. Oh, point is most of the time I cannot see you because in my window it's just a whiteboard window. So when I ask something and try to interact, please respond by like turning on your microphone. Otherwise, I won't get it. So if you do not have much noise around you, please keep your microphone turned on. That's better. Also, pardon my bad English. So pardon me for my bad English, but yeah, this is all I have. I can offer this only. Okay. Now we have seen one-dimensional systems, but what about two or three-dimensional systems? Like the surface of this this whiteboard window. So we need actually two independent parameters to reach each of the points. Like we set up a coordinate, yeah, in one direction. In like we set up a coordinate, we usually call it like this kind of rectangular coordinate. We call it Cartesian coordinates. So okay, my bad drawing. Okay, so we associate two numbers to each of the points, like x1 comma y1. So what does it mean? It means we have actually parameterized along two directions. So in one direction we have parameterized like this. So it's not just along this line. Actually, this parameterization is everywhere. So if I like extend these small lines, so it will just fill the space. So all we have done, like we have parameterized in x direction and also parameterized in y direction as well. So in two-dimensional system, like the many number, like we need two numbers, two unique numbers here, like two independent numbers to recognize or like to assign to each of the points. So that's the dimension of the system as well. Like if we have a three-dimensional system, we need at least three numbers. That's what I'm saying. If it wasn't clear here. Okay. So now we all, I can assume that all of us know everything, almost everything about Cartesian coordinates, right? So we can like talk about Cartesian coordinate like without much explanation, right? Everyone knows that, right? Okay, great. So in Cartesian coordinate, we actually parameterize our space rectangularly. That means each of the axes, they are perpendicular to each other, and if you go to in any other point, like at that point, that coordinate lines, they actually I'll introduce the concept of coordinate line a little bit later. So coordinate lines, they actually lie along like this and that. So that's what our Cartesian coordinate is. So we'll go deeper into that later. Okay, so let's talk about rotation. That means in general, we want to talk about transformation of coordinates, but the rotation are one of the simplest way of like introducing these things. So that's why we are trying to introduce rotation first. So let's say you have assigned a number like a pair of numbers. At this point, the coordinates are x and y, and this is our x-axis, this is my y-axis. Now, how about we set up a new coordinate? This one and this one, these are the axes. So we call it x prime and y prime. Actually, I'm trying to write capital, not small. And in this new rotated system, the coordinate of this point is x prime comma y prime. So our question is, if this angle is theta, what's the relation between x, y, and x prime and y prime? Do we need to derive it, or we can just write it?
I think there's a 2x2 rotational matrix for transforming the coordinate system.
Okay, yeah.
I think, as far as I remember, the transformation matrix is cos theta, sin theta, minus sin theta, and cos theta.
Cos theta.
Then sin theta.
This one sin theta.
Yeah,
This
1 2 1 2 1 2.
This one. Okay.
Yes, yes. Sin theta
This minus sin theta.
and cos theta. I think, as far as I remember, I might
Yeah,
have
yeah, it's correct
fumbled
actually.
the minus sign.
Yeah, because your x prime, it's still like here. So any point on this should have like positive y and positive x coordinates. So yeah, it's cosine theta x, sine theta y. Yeah, it's correct. Or is it? There should be a minus here or plus here. Let's just
I
do
should have
right?
inversed the 2x2 matrix.
Let's derive this, right?
Okay.
So how do we derive it? So make a projection on the x-axis, right? So this much is our x, and this height is our y. So all we need to find, we actually need to find like the coordinate x prime or y prime. So we need actually this one. So this point is our x prime, right? So all we need to know the coordinate of this point x prime, right? So how do we do that? So we take projection on this one and that one, and this angle is theta, and we can see that this length, this is the hypotenuse, right? So x prime, actually, what's the definition of sine theta? Like, what's the definition of sine theta? Opposite is what here? It's y, right?
Yes.
And what's the hypotenuse?
X prime.
X prime. And what about the other one?
Cos theta.
The sine theta.
It's x prime cos theta, I think.
It's, sorry, did I made a mistake? It's a simple geometry. Okay.
I think we can just find the x cos theta and add it with y sin theta. I think that will be the easier way.
X cos theta.
And add it with y sin theta. I think.
So you need this amount, right? Like x cos theta would be like this amount.
X cos theta will be slightly smaller. I mean,
Smaller,
the
yeah.
90-degree will be on the X prime
Yeah,
coordinate.
that would be no. We actually need the other way, like the forward transformation will be like this one. Y prime equals to something, or X prime equals to something. That's what I need, right? Okay. Let's. Actually, I'm feeling a little bit nervous. That's why, like, it's this kind of simple thing is getting screwed up. Okay. How do I do it? This coordinate is X and this is Y. So actually, I need a relation between these two lengths, actually. This two length and this height.
I think we can use just Euler angles for this derivation, right? So in this matrix 1 1 position,
No. You do not use Euler angle. That's too much complicated thing. We are actually trying to just use simple geometry here.
okay, all right.
So how do we do that?
First, make a line which starts from point X and that's perpendicular to the line X prime. I think we should draw a line from which starts from point X and which is perpendicular to the line X prime.
Oh, here?
Yeah.
This point
Yes.
and perpendicular to that one?
Yeah, perpendicular to line X prime.
Okay, then?
Yeah. So that gives us the X cos theta. And then we need another one.
Okay, wait. So
yeah,
this
is
amount
X cos theta.
Yeah, this amount is like
The X cos theta.
X cosine theta, yeah.
Yeah, now we need the Y sine theta.
Y sine theta, right. So our Y is this height. That means, sorry, not this
Y is
height.
actually taller, yeah.
Yeah, this one. Actually, yeah.
I think if we just shift the Y.
No, we do not need that. So this angle is how much? I think
that's 90 minus theta, I guess.
No, theta.
Maybe theta.
This
That's
is 90 degree. So this is obviously theta, right? This one is theta. This one is theta as well, right? Because this is the perpendicular on this line. So this angle and this angle are obviously same. So if you do the analysis, so this is 90 degree, this is 90 degree. So this angle has to be equal to this angle. So this angle has to be equal to this angle, right? So say this one is y1 and this part, like this part is y2. Then y1, how much is that? It is
then y1 sine theta plus y2 sine theta equals y sine
y1
theta.
sine theta plus y2 sine theta would be the rest, right? This part. So, and also like we need that other part, like plus x cosine theta. Like seriously, this is a simple geometry. We did the probably the most in the most complicated way we proved that. Okay. So y1 and y2, we can see from the diagram that this plus this equals to y. So it's y sine theta plus x cosine theta. And how much is that? This is the x prime, right?
Yep.
So yeah, our formula is correct here. Like this matrix multiplication, we can do that. So x prime equals to x cosine theta plus y sine theta. So point is, when you do this kind of coordinate transformation, that means from one coordinate, you go to another, the number associated with each of the axes, it changes, right? That means the label of that point, it changes. So let me clean this thing up and then we'll talk. Let's redraw again. So in one coordinate, say in S coordinate, it was x comma y, but in another coordinate, this S prime coordinate, its label is now x prime comma y prime. But both of this label, they represent the same point, right? So providing just the label is not everything. So we need to know like how the coordinate was set up. So that's another important thing. So in Misnathon and Wheeler's book, it was compared like a telephone number or the address of your home. So say like the city corporation or municipality, they want to like assign each of the unique number, like each unique number to each of the houses, right? So they assign some numbers, like 1, 2, 3, 4. Like say you have a number 4 as associated with your house. So now probably for some unknown reason they want to change it. They want to redo it, and they have a new number for you. Point is, in both representation, in one representation your house has 4, number 4 associated with your house, and another is 6, but both of these things represent the same house. So another thing we need to know, that is what's the conversion between these two. So how to change that 4 to 6. So here we have actually found that kind of conversion. So it converts this xy coordinate into x prime and y prime coordinate. Is that clear enough?
Yeah.
Okay, so now in Euclidean geometry, using this Cartesian coordinate, we have an important notion, that is notion of distance. So already we know that this distance, is d, that is by Pythagorean triangle, it's d square equals to x square plus y square, right?
Yeah.
Yes.
So when we change the coordinate, so we go into x prime to x prime y prime coordinate system, then everything changes, but this distance shouldn't, because it's something physical, right?
Yeah.
So we should demand this thing as well. So you can prove it from here as well. You just take like the formula for x prime and formula for y prime and substitute it here and do the algebra. You'll find that it reduces down to x squared plus y squared. Right?
Yep.
So you can do that, right? Yeah, it's not a problem, big deal. Okay, so distance is something, even if you change the coordinate, that number, that distance, it doesn't change. So it gives rise to an important concept of the scalar quantities. Scalar quantities are those things that it has a number associated with it, and when you change the coordinate, that number doesn't change. Say you have a temperature like 30 degrees centigrade over here. Even if you change the coordinate, rotate the coordinate, that 30 degrees centigrade doesn't change. So, okay, you might say that I can change the coordinate in like temperature, like I would convert it into like Fahrenheit, but that's not what we're saying. We're saying the change in the coordinate of space itself. It's space only, not the other thing. By changing coordinate here, we mean like changing the parameterization of the space itself. Is that clear enough?
I have a question.
Sure.
I thought the things that doesn't change in space are called space and time are called invariants, because in space
Yeah,
there are
scalars are
length that
invariant. Scalar are invariant quantities. Yeah. So I said like it gives rise to a notion of something.
okay.
So we can generalize this idea like uh, there are numbers that doesn't change. So we can go out and find like which numbers doesn't change.
And those are called invariances.
Those are called invariances. Yeah. Scalar are invariant. That's the point. Like scalar is a special class. Is that clear?
Okay.
Actually, by scalar we mean scalar fields. So that's why it's a specific class. Otherwise, if we were talking about just numbers only, then you wouldn't distinguish between these two. Okay, so how do we define our scalar quantities? Scalar quantities is like this. Consider we have a quantity phi, and it's dependent on the coordinate x comma y, and it goes to some phi prime when you change the coordinate. By ct here we mean coordinate transformation. So this phi prime is now a function of x prime and y prime. But to be scalar, the number has to be the same. So like by the definition. So the definition of a scalar is this. So any quantity that changes like this, or in other words, the number associated with doesn't change, we call it a scalar. Or actually scalar field. Here it's a function of x and y, so it's a scalar field.
Yep.
Okay, so we'll talk about scalar and vector later, but first we actually discuss a little bit more about this distance, because these distances are important quantities in GR. So say we set up a new coordinate, a polar coordinate here. You all know about polar coordinates, right? 2D polar coordinate. So this point is represented by r and phi with the relation that that is connected by this. Like here, if we had like previously the Cartesian coordinate, this x is r cosine phi and y is r sine phi. By this formula, these two are connected. So how we like geometrically represent this thing? We say that this distance, it's represented by r, and the angle between this direction and the x-axis, it's represented by theta. Well, that phi. Okay. So now we are in a new coordinate that's like this. This point has a label r comma phi. Now this distance, like even if we go in polar coordinate, this distance, that d, it has to be remain fixed, right? Under this transformation, it has to be the same.
Yes.
So then in polar coordinate, what would be the formula for d?
Is equal to r.
Equals to r. I'm actually talking about d square. So d square equals to r square in your language, right?
Yes.
So why not it's this? Because we had this structure here. So what's so special about?
Well, we can rotate we can rotate this, and by rotating, theta will be changing, but the length will not change. That's why it will be independent of theta.
Okay, yeah, that's a great argument. Yeah. So D has to be independent of phi, because if you rotate it, phi will change, but D should remain same. So obviously it shouldn't be dependent on phi. But point is, there is some specialty about like this Cartesian coordinate, because it has this specific form like distance in only in Cartesian coordinate. In other coordinate, this formula changes. So in any coordinate system that you set up, you have an assigned way of like measuring distance. It'll be become transparent later. It might not be transparent at this point, but so
Yes.
okay, so I can proceed, right? Like it has, as I said, like it has some assigned rule that how you measure distance in that coordinate. And later we'll see that in Cartesian coordinate, like it's kind of a special coordinate. It's very special than other. Things are simple in Cartesian. We'll see that later. So the point is, whatever coordinate you say, they provide you, like they provide you this coordinate system. Like this is xi and this is zeta coordinate system, and this point is represented as xi comma zeta. So tell me what's the distance is. What's the formula for D?
Is it Cartesian coordinate?
We do not know what coordinate it is. So yeah, but one thing, like this line is straight, this line is straight, and this angle is by drawing it's 90 degree.
Okay, then xi square plus zeta square.
So your assumption is D square would be xi square plus zeta square.
Yeah.
Now say that actually I did a trick on you. So basically what I was trying to represent here was my R direction. Here was my phi direction, like phi coordinate. Like remember, R and phi are just two numbers. So how we like we could like say that this distance is like I'm not talking about distance, like this space, like the previously R phi space is mapped into here such a way that it becomes a rectangle. Like this phi runs from 0 to twice pi, and this R goes to infinity. So this is
At the
my
first example, for polar coordinate, phi was not a length; it was just the angle. That's why we could not apply the Pythagorean theorem.
Yeah, we cannot apply the Pythagorean theorem. It's not just that phi was not a length. Even if it were a length, you cannot say this because it could be scaled.
Okay.
We'll see this kind of examples later. So point is, to know this distance, like what's the formula for distance in terms of coordinate, you need to know precisely what the coordinate system is. So this gives rise to an important concept of metric tensor. We'll see that thing later. So that thing is actually associated that with a space itself, and it tells that how to measure the distance. So in principle, if it was not something like some physical space, it's a mathematical entity like R and phi. So there is no way you can say like how to measure the distance, like say PV diagram, mathematically speaking. So we draw PV diagram all the time, say. So do you have a notion of distance from this point to that point? Do you? So remember, this axis represents the pressure and this axis represents the volume in this case. And it goes to infinity. Now it's just bounded by 2s5. Do you have a notion of distance over here? How much is d? Answer is you do not know. A mathematician can obviously assign a number, like assign a formula, like say our d is like this. D square is like v to the power 4 plus p squared, like this. A mathematician could say that, but physically it doesn't mean anything. So in physics we say that.
But it has to satisfy the dimension.
Yeah, you can have like a scaling factor over here. So you need to be a little bit more flexible about dimension. In a moment, we'll see that why. Otherwise, like GR would be a little bit complicated for you. So okay, so, you have a k over here, and that takes care of the dimension. Also, like L over here. These two things take care of the dimension. So yeah. So point is, you do not have a notion of distance over here on this space on PV diagram. So notion of distance is something unique. It's a very special property of a space. Not all space has a notion of distance to it.
Okay.
Okay. So let's go to the next thing. Let's talk about vectors. Oh boy, I've already spent 1 hour. We saw that there is a definition of scalars. Scalars transform like this. Phi prime at x prime comma y prime equals to phi at x comma y. So before going to vector, we'll define the mathematical entity as vectors, like what do we mean by a vector and vector space. So vector space, we know, we all know that it's defined by some rules that if you have a space V, like that holds all the elements, it's a set of, it might be infinite set. Actually, it is an infinite set of some quantities. We are talking about two typical elements, say A and B. So we perform operation between these two and determine like if V is vector space or not. It's defined like this, like addition has to be defined, and that addition has to be again an element of V. Addition has to be commutative. What else? For another typical element C, this has to be associative, right? What else?
Distributive.
Distributive. That's the multiplication identity. So we'll talk about that later. So the next two additive thing are like there has to be some element null or
Scalar.
zero.
Yes.
It's the identity of addition actually. So there has to be some element 0 on this V, like this thing has to be an element of V such that if you add anything with that, that gives you that same element again. And for each of A, there has to be some, for example, for say D, there has to be some D element for each of A such that A plus D equals to 0. So we call that D is actually, it's a notation that is, we call it this D as negative of A. And what else? For multiplication, we have few more, but the basic idea is this. It can generalize everything. that is distribution of multiplication, that is this thing, and multiplication of scalars, that is m times m times
The scalar identity of multiplication.
this thing. This thing has to be satisfied. If you have only this thing, you can do any operation on the vector space. So if you are talking about some vector that has to satisfy all of these properties, is any of this is violated, then that doesn't form a vector space, and you're not talking about vector. So let me clarify a few things. So, whole differential geometry is all about vector spaces. So every element, everything we'll talk about will satisfy all these things, except for few.
Okay.
So
The last axiom or the 10th axiom of the vector space is actually both sides of the equal sign are same. Both sides of the equal sign are same for the last axioms.
oh, sorry. I made a mistake over here. Sorry, I meant this. Sorry. Is that cool now?
Okay.
Okay. So in whole differential geometry, we'll talk about vectors. So probably you have heard terms like one forms, tensors, and many things. Point is, all of those things, they form vector space. Mathematically speaking, they are vectors. They form vector spaces, but we still classify them because of their transformation properties. So here, when we do differential geometry, we have an extra additional notion of like imposed notion here, what we mean by vector. So let's see that. Here, all vectors are actually modeled after some special things, that is position vector, we call it, defined as this thing. It's a vector element whose elements are like coordinates of space written in Cartesian code, like elements of Cartesian coordinates. So for 2 points, like on any space, you take 2 points, R1 and R2, and you can prove all of this thing out of it. So point is that means our representation, like Cartesian coordinate representation of a point, is a vector. Yeah, mathematically speaking. You can prove that. That's a pretty easy thing. Obviously, if you add 2 points here, actually the addition is defined like component-wise addition. It always remains in V. Yeah, it's commutative and it's associative and all that. If you have a null point vector here, for each of the vector you have a -1. So everything satisfies. So our position vector, like a point, say point P, actually for point, when I write, I'll try to write as a tilde. There is a reason, it will be clear later. So this point, when it is represented in Cartesian coordinate, that is a vector. So this R is actually represented in Cartesian coordinate explicitly. It doesn't hold in any other coordinate, so that's a specialty of Cartesian one. So that's some part I was talking earlier. So you can take it for polar coordinate as well. Say for polar representation, you have you have a point like 2, 3/2 pi. Is that a valid point?
Yeah, I think so.
And say you have another point like 2 comma pi. That's also a valid point, right?
Yeah.
But if you add those two, like if you define your addition by just adding component wise, then what it becomes like 5 by 2 pi, right? Is this a valid point?
No.
No. Why?
Yeah.
Because non-linear coordinates.
No, because your second coordinate,
5 by 2 pi is not defined there.
yeah, it's 5 by 2 pi is not defined, right? So that thing that doesn't form a vector space.
Yeah.
So point is point in a space. Point in we'll call later it as a flat space. By flat space we mean that where Euclidean geometry is valid. So when Euclidean geometry is valid, then Cartesian representation of a point, Cartesian coordinate representation of a point represents a vector. So that's the specialty of Cartesian coordinate. So from now on, when we talk about vectors, we'll talk about in terms of transformation rules. Why? Because these are, it changes very specific way when you change the coordinate. Like when you rotate it, you saw that like your x prime comma y prime, say that this is my r prime, and x comma y, this is your r, and they have a very specific relation when you rotate it, right? Like cosine theta, sine theta, cosine phi, sine phi, sine theta, sine, minus sine theta, cosine theta on R, like this. So in general, this point in Cartesian coordinate for some arbitrary transformation rule, we can actually generalize this idea as like this. Like this is x coordinate, y coordinate, and there is a matrix, 2 by 2 matrix in 2 dimension that works on this x and y. So say this is our lambda 1 1, this is lambda 1 2, this is lambda 1 3 2 1, this is lambda 2 2, right? We call this thing a transformation matrix T. That transformation matrix has a specific formula. We'll talk about it later, but remember, we call it a vector. Here we call it a vector when the transformation rule has this specific structure that actually I call T is like this. If any quantity that follows this kind of structure, we call that as a vector, because all other vectors is modeled like the point in space represented in Cartesian coordinate. You get that?
Yeah.
So from now on, we'll say A is a vector if and only if when you change the coordinate, A transforms like this. A prime becomes like this. If this thing is satisfied, also like that mathematical thing has to be satisfied. These two things has to be satisfied.
Is there any restriction on T?
Restriction on T? Yes. Yes, there is a restriction. There is a restriction. We actually want our distance to be invariant, right? Like this, when we change the coordinate, this the norm of r prime. Actually, I haven't discussed norm. That's why I'm not saying it. But
Determinant of T should be one like that.
Yes, yes. So norm of this thing has to be fixed, has to remain fixed. So norm of this, like determinant of this matrix has to be plus minus 1. There is a case where it can be minus 1 as well. Okay. So is it good up to this point?
Yes. Yes.
Okay. So I think we should take a break for 10 minutes. Actually, every hour we are supposed to take a 10-minute break. So this is the time now. I'm a little bit late. 10 minutes, after 10 minutes we'll start it again. Now we can discuss. If you want to go to the like washroom or something, you can go, and if you want to grab a coffee, you can, or you can continue discussion with other like your peers. That would be fine, or with me. So this class is going to be a little bit elementary. Like actually, it's most elementary lecture throughout this course. So be patient. Be a little bit have a little bit patience. Otherwise, like I know everyone knows this kind of stuff, and I also do not like teaching this kind of thing. These are boring.
Deep, hi, are you there?
Yes, I'm here.
Okay, I have a question. So you have defined a vector space by 10 set of axioms, and you wrote the plus sign by defining an operation. Is it an in general operation or just the addition operation?
No, it's an addition. We call it addition operations, but you have to say like how do you add two things, right? That's your definition of addition.
Okay. Uh,
Oh boy, there are a lot of things. I have to be a little bit faster. I'll just go for a moment and come back.
Is anyone here?
Yeah.
Okay. I have a question. We can see that a vector 4 and 5 by 2 pi. My question is why it is not considered as a vector?
Oh, because your range, like your R and phi, it has a specific range. Like your phi can go 0 up to twice pi.
Oh.
So
Well, but
phi,
can't
phi
we
to pi is not been defined.
define is using modular arithmetic like pi
Oh,
by 2 is equal to
yeah, it becomes something. Yeah. So when that thing is satisfied, like the first one, then due to its nonlinearity, the later thing, like commutativity, break.
I think
So
the
I have
main
chosen.
problem is well there may be several problems if we want to define it as a vector space. The main problem is defining the inverse, additive inverse.
Yeah,
we
that's
we
all. That's
we
also a
can get
problem.
a unique inverse here.
Unique solution. Okay.
Yeah. Yeah. So actually, like I have chosen a simple way to show that. Like there are a lot more problems. So apart from Cartesian coordinate, there is no other thing like no other coordinate system that in which the representation of a point becomes a vector. So I've just chosen a simple one just to illustrate.
Okay.
Uh, 3 minutes more, then we'll start.
I had a
Are you guys
question.
bored?
Hello.
Yeah, sure.
Do you,
Go ahead.
Yeah, I was thinking that if we define the addition differently, can we then consider those as vectors? What if
No.
we just don't add the r and the thetas? What if we add them differently?
Yeah, that could be a possibility. That could be a possibility. Yeah.
That's why I asked the operation of the vector
Yeah.
spaces, right? Change
It's
the
like
operations definition of
usually
mechanics.
usually here it's we mean like the addition we here we mean like addition by components, right?
Yeah.
So if you go to a math like algebra textbook, you'll find example that like counterintuitive thing can be vectors as well. Really counterintuitive things.
So in
So,
that
but
sense, I mean, can those coordinates be considered vector if we
yes,
change the
yes,
addition
yes,
operation?
yes.
Okay,
You have to
that's
change the
interesting.
addition operation itself. But what's the point of it when you do not have a like geometric meaning to it, right? What's the point of doing that? Here we are doing because it has a direct geometric meaning. Component wise addition means something. Okay, 1 minute more. Okay, so we have a okay. Can you start now? Like our break is over, I believe. Hello, is everyone back?
Yeah.
Let's ask each and everyone again. Ankan Dash. Arafat
I'm here,
Hussain.
sir. I'm here.
Arafat Hussain.
Yes, I'm here.
Yeah, I can see Dr. Friedberg. Durjoy.
Yeah, I'm here.
Humaira.
Yes, I'm also here.
Jaber.
Yes, I'm here.
Juthi.
Yes, I'm here.
Love. Okay, I think she isn't here. Pooja. Prashanto.
Yeah, I'm here.
Robin.
Yes, I'm here.
Sifatul.
Yep.
Sulaiman.
Yes, I'm here.
Imad.
Yes.
Okay, great. I think we start now. So we have a notion of distance in a Euclidean space, right? So that we can generalize, give rise to a concept of dot products. So here our distance squared is in 3 dimension, it would be like x squared plus y squared plus z squared, right? By Pythagoras' theorem, right?
Yes.
We can think of like this. It's basically a product between two position vectors like x, y, z, and this x, y, z, right? You can think of like that. So in that sense, our d squared, it becomes an object such that it takes two vectors like 2r and produces some number. So that number is this. Say your d squared. This d square, it basically an operation in general, like you substitute like r square, like r in two slots, like it takes 2r and produces a number. It takes two position vector and produces a number. Those same position vector.
Yeah.
Which is actually defined like this. For the first one, first position vector, if you represent it as a column matrix, then you have to make it as a, you have to transpose it and multiply with other.
Yeah.
So we call this operation as the dot product. So when writing this, we write is the, like this. So you can think of like dot product is basically a notation for this d square. So dot product.
Well, we are assuming that the field is not complex here.
No,
yeah,
no, it's not.
real. Yeah, okay.
It's real. Like in GR, mostly we'll talk about all real things.
Okay. Okay.
So yeah, you wanted to do a complex conjugate over here, right?
Yes.
Okay. No, we are not dealing with complex things because those are more complicated. Okay, so this dot product is, this dot is basically notation for this d squared. So it has two slots, here one and here one, In one slot you substitute r, in another one you also substitute r and get that number d square, right?
Yes.
So this dot product is defined as, this dot product with two slots is defined as, so for the first slot you have to take a transpose and multiply with the second one. This is the basic idea.
Yes.
So now for any vector dot product is defined like this. Any two vectors, because you have two slots, you can take two vectors. So dot product is defined like this. You can say is like d square, it takes two things and produces that number. Also, you could say this is basically one of, it has to be transposed and multiplied with other ones, right? So dot product is basically a generalization of that distance notion. Actually, this distance is much more like geometrical concept than you can imagine, like probably the most important concept in GR. So this d square is actually the metric tensor, we'll call it, and that will define the space time. So how two vectors are dotted with each other, it's the most important thing in GR probably. So it's not that simple. Okay. From this definition, we can define a concept of norm. Norm of some vector is defined as, when you do this operation, it gives you a number. And that number is defined as, like, you have to take dot product between the same vector and take square root. That's how we define norm. Basically, norm of a position vector is defined as this distance d. We have been talking about, right?
I have you listen 2 dash double dash both side.
Where?
Well.
Okay. Yeah. So yeah, 2 bars you mean, right? Like.
Yes.
Usually norm we write like this, but here we do not have any ambiguity with that. Like usually we single bar we mean the determinant, and double bar we mean the norm, right?
Yes.
But what is the determinant of a vector? It's not even defined, so there is no ambiguity. That's why we can use that without a major confusion. And in any GR book or any physics textbook, you'll find this notation usually, like single bar, not double one. But yeah, mathematically speaking, like math people, they tend to define like with a double bar. Okay, so it gives rise to a concept of a magnitude or norm of a vector. So as we have a norm, we can normalize things. Normalize means we can divide by norm, right? So for any vector A, we can have like this vector A, divide this thing by norm of it and multiply by norm of it, right?
Yeah.
This thing is a number, and this thing is still a vector. We call it a unit vector because if you take norm of this thing, the norm is always 1. You can take it like, if you take norm again, it becomes norm of A by norm of A, and that's 1. So that's why we call it a unit vector, a vector which has a norm 1. And the number we have in front of it, it's the magnitude of a vector or the norm of a vector. So in this this expression, like norm of R, it actually specifically represents the distance between the center and that specific position in the space. Okay, so we already know the concept of like dot product and like what it means. So we know it means as the projection of one vector into another. so let's not talk about it, but let's talk something about like the modern notation we'll be using. So here in GR, it's sometimes really difficult to work with full form. Full form means like this kind of form, like when you have a bar on the like you're dealing with full object. So in like within 4 or 5 lecture we'll encounter like there are standard 3 representation. One is like pictorial, we can draw diagrams of the geometry, and there is a like abstract form, that is we have written like full object like this A and B, and there is a component form. That's actually the most useful thing, because when computing something we need the components. So we'll be using a lot about components later, so that's why we are using this notation. So dot product between these two vectors, if you look at the component, you can realize that it's basically what you need to do. Like, let's assume that it defines this. So let's assume that they have a like 3-dimensional representation. So you have like say AX, AY, and AZ. You need to transpose one of those and then multiply with another vector like BX, BY, BZ, right? What do you get from this? So it becomes like AX, AY, AZ, transpose one, and this the column one. So multiplication this row matrix and this column matrix gives you AX, BX plus AY, BY plus AZ, BZ, right? So that's in component form your dot product is, right?
Yeah.
Well, isn't it true for orthonormal basis only?
Yeah, we are talking about Cartesian coordinates, like we talked about Cartesian representation. So we'll generalize this idea. Okay. We haven't generalized that. So here the D, look, you should have asked this question when we wrote this thing, when D squared is defined like that. Okay, so yeah, we'll encounter more kind of forms of D, so that could do more kind of operations. But when we are everything representing in Cartesian coordinate, we have this specific form.
Okay.
So it'll get generalized pretty soon. So, but there will be something more. That's the interesting part. Oops. Let's take over here. Maruf, are you here? Maruf, are you here? Jabir, can you hear me?
Yeah, I can.
Could you please phone Maruf and and ask him if he's continuing recording or not?
Okay, I'm asking.
Okay, so in component form in Cartesian coordinate, we have this, the dot product has this specific form, but it's not like easier to handle mathematically. So we use a different notation. Instead of writing AX, we will write A1. Instead of writing, actually, I'll write here as this. I'll change this later. So AY equals to A2 and AZ equals to A3. Similarly for B, BX equals to B1, BY equals to B2, and BZ equals to B3. With this notation, we have this dot product A1 B1 plus A2 B2 plus A3 B3, right? So this thing becomes sum over sum I, which runs from 1 up to 3, AI BI. Really compact notation, right?
Yeah.
Compact and neat notation, but we are still not happy with that. Later, we'll introduce, like when you have repeated index, you do not write this sum explicitly. You need not to write this sum explicitly. We understand that there is a sum when you have repeated index. So that's you call as Einstein summation convention. We are going to use it later. Okay, so one important property of dot product is that it's symmetric. That means A dot B equals to B dot A as well, right? We all know that, and we can easily prove this. You can just verify it, and actually this formula you can see easily. Okay, now we know the dot product. What about the dot product between the bases, particularly the basis vector in Cartesian coordinate? So in Cartesian coordinate, we have 3 bases, right? So we call it E1. This is 1, 0, 0. Then we call it E2, which has a representation of 0, 1, 0. And we call it E3, which has a representation of 0, 0, 1. Right?
Yeah.
So what happens when you take dot product with E1 with E1? What happens? So all you have to do, you have to take this thing. And you get 1, right?
Yeah, for same we get 1, and for
yeah,
different
so
we get 0.
Yes, for same we get 1, and for different we get 0. That's the important thing. So we can generalize this thing into like this: EI dot EJ. What is this thing?
Kronecker delta IJ.
It gives you 1 when I equals to j, and it gives you 0 when I is not equals to j. As this is kind of a special thing, like it has a very special place in GR. So we have a specific notation for this as well. We call it Kronecker delta. So with this Kronecker delta, so like I'll rewrite it. I'll write it again. So with this Kronecker delta, actually you have defined your dot product, right? We'll see later that basically this Kronecker delta here in this specific case of Cartesian coordinate, it's basically the components of your d squared object, distance squared object. We'll see that later. Okay, so this Kronecker delta can be used as like we can see some operations of Kronecker delta as well. So what happens when you have like this? So sum over j Kronecker delta ij aj. What happens? What do you get?
I will get AI just.
AI. Why?
Because when j is, well, Kronecker delta just change the index of the of a. Because when j are same, it will give me 1.
Yeah,
and when
you can expand it and
j are same, it will give me 1. And otherwise,
like
it will be
like this thing is like Kronecker delta I1 A1 plus Kronecker delta I2 A2 plus Kronecker delta I3 A3, right? This thing equals to. So I cannot be taken like I cannot be any value, right? I have to be something 1, 2, or 3. If I equals to 1, you get this part only, and this thing becomes 0. Also same thing for 2 as well. You get this part only, and the others are 0. So whatever the I is, you only get that part only, right?
Yes.
So if I is 1, say for I equals to 1, you get this thing equals to delta
A1.
1 A1, which is A1. So whatever the I is, the final index of A is that. So that's why we have this thing, and this is gonna be really important, like some summation over Kronecker delta. Okay, another important thing we need to know right now is sum over 2 Kronecker deltas. Like what happens, like delta ij, delta jk, and you have a sum over j.
I will get delta ik. Just
Why? The same argument, right? You'll get
yeah.
delta ik. So remember, when you have a delta, Kronecker delta, and summed over one index, that sum index is called dummy index, is just changed with the other one that is not summed. So here we have done that thing. So j is replaced. This j replaced with this j is replaced with that I. That's the thing, or you could say in opposite way. And the final thing we are going to know is what happens when you have Kronecker delta I sum over I equals to 1 up to 3. What is that?
Just 3.
Yeah, how?
3. It will be 3.
1 or is it 3? Is it 1 or is it 3?
It's
3. Why 3?
Delta
because if you
1
expect
delta
just delta 1 1 plus delta 1 2 delta 2 2 plus delta 3 3, right? So
each of them
delta
is
1
1.
1 2 is 1 and 3 3 is 1. So that's why you get 3. So when you have summation on delta, so that actually that in each of the index of delta runs for each of the dimension, the number of the dimension. So we are working with 3 dimension. That's why it runs from 0 or 1 up to 3. So for n dimension, it will run for 1 up to n. So when you have summation over 2 indices of delta, then you get the number of the dimension. Got it?
Okay.
Okay. Finally, we're ready to talk about cross products. I think I should clear the canvas, otherwise it's getting messier. Okay. Yeah. So cross product, it's an antisymmetric product, and it's defined only in 3 dimensions. You can extend the definition, but that's not a straightforward extension. So let's write it as like this: sum A cross B. This cross is our operation, like the cross product. Cross product is also a bilinear operation. That means it takes 2 input and linear in each of those. Like our dot product was bilinear as well, remember? Bilinear means it's linear. It has 2 indices, like two slots. It can take 2 objects, and for each of the objects it's linear. Okay, so it's also a bilinear operation, and it takes 2. Obviously, it takes 2 vectors and produces a vector. So this kind of specific definition, it's only possible in 3 dimension. Cross product, how it is defined, that's the important thing. Cross product, this thing, it's defined as if for our A represented in Cartesian coordinate, we can write it as like this: I equals to 1 up to 3 AI EI, right? For B, you can write it as this as well.
Yeah.
Everyone cool with that? Happy with that?
Yeah.
Okay. So our cross product, it is defined is, so A cross B is defined as sum over J. Actually, no, sorry. Sum over I equals to 1 up to 3. Sum over J equals to 1 up to 3. Sum over K equals to 1 up to 3. Epsilon I J K EI AJ BK. This is how it is defined, where our epsilon is like this. It is +1 if I, J, K are even permutation, we call it. Remember the word even permutation. It is -1 if it is I, J, K are odd permutation. Odd permutation. And 0 otherwise. That means for all other combination, it's 0. This is how we defined our cross product. Familiar definition, right? Or not? Do we need to convince ourselves that it's our usual cross product?
Yeah.
We need to convince ourselves, right? Okay. Let's see. So previously we, from probably 11th or 12th grade, we learned our cross product like this. It's basically
The determinant of a matrix.
No. That's the mnemonic. I do not want to write that. So, okay, A1 B2 minus A2 B1 into E3, right?
Yeah.
Plus A2 B3 minus B2 A3 E1 plus A3 B1 minus A1 B3 E2. This is how we defined our cross product. And it has a geometric meaning. It's a very geometric meaning because A cross B, it actually represents the area spanned by the vectors, two vectors. So we already know this thing. So I need not to like explain everything here. So it can represent this area as a vector. So it has a direction of the perpendicular to each of those, and the magnitude is actually equal to this area, right? We already know that. And norm of this
well, in your previous definition of cross product, there should be a unit vector, I think.
Okay, I have an unit vector here, EI.
Oh, thank you.
Okay, let's we'll convince ourselves. So norm of A cross B, we already know. We need not to like re-explain it. It's AB sine theta, right? Where theta is the angle between, like, the smallest angle between these two. We already know that. So that's like, you are already advanced students. So we need not to explain everything. So let's convince ourselves that this definition known from childhood is actually the same as this one, provided that epsilon is defined as like this. So it's a little bit hard to see, but let's just seek for one component. So what about oops. So this thing, actually I need to rewrite it, otherwise it's hard for me as well to Can you read my handwriting?
Yes.
Yeah, clear. All right.
Is that okay? This is what I wrote earlier, right? So expand the sum over I. So if you expand that, that gives you epsilon 1jk ajbk E1 plus epsilon 2jk ajbk E2 plus epsilon 3jk ajbk E3, right?
Yeah.
So let's check that if this part is equals to that part, or so on, like this part is equals to that one. If we just check just one of the components, it will be fine, right? It's basically cyclic, so
yeah,
we need not to worry about everything, just one part. So let's try to convince ourselves that we need to show that epsilon 3jk ajbk, it's basically what? That part, a1b2 minus a2b1, a1b2 minus a2b1. Right?
yeah.
So if you expand this thing, you get like there is a sum. Remember, there is a sum over j, there is a sum over k. Okay, if you actually I'm not writing the sum. You probably noticed like I have dropped the sum already. Each of the term you have like jk, sum over jk. You have sum over jk. So remember that there is a sum over jk. Okay. So if you expand the sum over j, what happens? If you have your sum over k and you are expanding your sum over j, so it gives you epsilon 3, then 1k a1 bk, right? Plus epsilon 3 2k a2 bk plus epsilon 3 3k a3 bk. Do you agree with that? I just expanded the sum over k, sum over j.
Yeah, repeated indices gives
Yeah,
0.
repeated index vanishes. So this thing is 0 by definition of epsilon. So we have this epsilon 31k a1 bk plus epsilon 32k a2 bk. Right? Now we can expand. Now we can expand the sum over k as well. So if we expand the sum over k for the first term, it gives you like epsilon 311 a1 b1 plus epsilon 312 a1 b2 plus epsilon 313 a1 b3, right? And for the second one, what do you get? Someone please tell me.
Epsilon 321 A2 B1.
A2 b1 plus
by using the same argument, we can actually remove epsilon 311.
for the next step we'll do that.
Okay. Epsilon 322
322 a2 b2 plus
epsilon 323 a2 b3.
A2 b3, right? So for the same argument that when you have repeated index, it gives you 0. What else? It gives you 0. It gives you 0 and it gives you 0. Right? You're left with only two terms, this one and that one. So what is, oops, it's behaving weirdly. Okay. Okay, so what is epsilon 312? Is this permutation even or odd?
It's even permutation. 312.
It's an even permutation. It goes like 312, right?
Yeah.
So it gives you plus 1. That means A1, B2. And this one, epsilon 3 to 1. What is this?
It's an odd permutation.
It's an odd permutation. It gives you -1. So minus A2, B1. So is this the thing we have been seeking for?
Yeah.
A1, B2 minus A2, B1.
Yeah.
So we have successfully convinced ourselves that the definition I gave at the beginning is the same definition we knew from the childhood, right? It's the same definition.
I have a question.
Yeah,
I'm
sure.
getting some problem with even permutation. Yes, I cannot understand that how epsilon 3 to 3 is 0, or why some.
It's the definition of epsilon. We have defined epsilon such a way that when you have even permutation, it's 1. When you have odd permutation, you have -1 or otherwise 0. What we mean by
you did not define even permutation.
Yeah. What we mean by even permutation.
Yes.
Even permutation means even to this one, 1, 2, 3. Anything, any permutation you can get by 2 successive switching of 2 indices, that is even to this permutation. And if you can get odd number of permutation, you can get something to this one, that is an odd permutation. That means when you have like say 3, 1, 2, how many permutation you need? You need 2 actually. You switch 2 and 3, and then it becomes like 1, 3, 2, and you switch between 1 and 3. That gives you 3, 1, 2. So you need even number of permutation to get that from initial of 1 to 3. Or odd permutation, we need odd number of permutation to get that. For example, to get 1, 3, 2, you need odd number of permutation. That means you needed 1 permutation.
Now I understand.
And anything that you cannot attain from permuting just 1, 2, 3, that is the otherwise thing. That means when you have like 2, 2, 1, you cannot get 2 to 1 out of this 1, 2, 3.
Okay, now I understand. Thanks.
Okay. Yeah, it's good. When you have any confusion, any problem, just ask. Probably some of your peer would need that too, right? I hate this software. Just give me a moment. The heck is this? Really, one person. Oops. Finally. Okay, so we have convinced ourselves that the previous definition we had is equivalent to the modern definition of cross product, that is sum over. Actually, I'm not writing the sum. You understand that there are sums. So epsilon ijk ei aj bk. That is our cross product. Okay, great. So there are some interesting relation between this epsilon and the Kronecker delta we learned earlier. So it's gonna be helpful later time, particularly when we learn exterior calculus. It will be extremely helpful. So let's study some. So do it as your homework. Like you can prove this thing, like epsilon ijk epsilon lmn. If you take that, this is basically a determinant of Kronecker delta IL, delta IM, delta IN, delta JL, delta JM, delta JN, delta KL, delta KM, delta KN. the determinant of this thing. This is called the famous Levi-Civita identity. Levi-Civita, I mean epsilon delta identity. Levi-Civita Kronecker delta identity. Okay, so I'll give you a hint how to convince yourself that it's true. So set ijk or element to something. Say like you set element to 1, 2, 3. So you are left with epsilon ijk, epsilon 1, 2, 3. Now you know, like you have said like L equals to 1, M equals to 2, N equals to 3. Now you know what your epsilon 1 to 3 is, right? You know that. What is that? It's 1, as it is an even permutation, right? So you're left with epsilon ijk. So epsilon ijk has to be equal to Kronecker determinant of Kronecker delta. I1 Kronecker delta, I2 Kronecker delta, I3 Kronecker delta J1, Kronecker delta J2, Kronecker delta J3, Kronecker delta K1, Kronecker delta K2, Kronecker delta K3. This thing. Can you prove that? Okay, let's prove it. Like, it's not gonna be that hard. So how do you take determinant of something? This thing multiplied by this determinant of this small matrix, right? So it gives you Kronecker delta I1, Kronecker delta J2, Kronecker delta K3 minus Kronecker delta I1, Kronecker delta J3, Kronecker delta K2. Then this thing plus Kronecker delta I2, Kronecker delta J3.
I think it can be easier if you use the properties of determinant.
How?
Like if for repeated index, we can show that any of the rows or columns are equal or 0. So the whole determinant is going to be 0.
Oh, yeah. You can do that.
Yes, and
yeah. Actually, that's easier. Yeah, I thought of it. Yeah. So all we need to show that this thing is actually it has that same structure as epsilon, right? So what if you have like an even permutation, like 1, 2, 3. So for an even permutation, we can see that we have which way it goes? It goes like this: 1, 2, 3, right? 1, 2, 3. So then
it will be an identity matrix.
Yes, it will be an identity matrix in that case. Yeah. So because like here it will be 0, here it will be 0. So yeah, for epsilon ijk it will be like determinant of 1, 0, 0, 0, 1, 0, 0, 0, 1, which is 1. So if you switch any of those two things, that's basically switching those two rows, right?
Yes, and it gives -1.
And that will be -1. And for any odd permutation, it will be -1. For any even permutation, it will be +1. And it can be easily shown that for any repeated index, actually two rows actually repeat, so it's 0. Right?
Yes.
Okay. Yeah, so I think we have convinced ourselves that Levi-Civita identity, like Levi-Civita Kronecker delta identity, epsilon delta identity is correct, right?
Yeah.
So remember this thing. It's gonna be really handy when we do some calculation regarding cross product and dot product. Should I show some calculation regarding these two, or should I proceed? Because I have a lot of things to teach. I'm actually lagging behind a lot. think one common identity we can show, like double cross identity. We already know that A cross B cross C, actually this thing, A cross B cross C, it's not associative. So yeah, what is this? Like, what's the result?
Backcap.
BSC CAB, right? Yeah. So B
Vector.
A dot C minus C
C A dot B.
A dot B. So can you prove that using this identity? Answer is yes.
Using Levi-Civita?
Yes. So we can write one of, like, just ith component of this thing. Just ith component of this thing. So A cross B cross C will be sum over I, EI, and
By as you have introduced I think as you have introduced to the Einstein summation convention, so you can give us the sum notation.
I think everyone is not okay with that.
Okay.
So I'm not sure. Like, it will be easier for me because it's hard for me to write multiple times. Should I give up Einstein sum convention? Like, should I adapt Einstein sum convention or not?
I think you should.
Anyone else? Two people are saying that you should. Okay.
I
Dr.
vote for
Friedberg.
yes.
Okay. Is there anyone who doesn't want it to or I think I can drop that sum signs, right? Yeah. So let's not bother about sum signs. We understand that as long as we have repeated I, it means it's summed over. Okay, great. So now we are talking about this ith component of this thing. So ith component of this cross product would be like, so this is one object and this whole thing is another object, right? So we can write EI, then epsilon I jk, oops, it's not epsilon lambda, epsilon jk. First object is A, so jth component of A, and then kth component of B cross C. So kth component of B cross C, like this.
Yeah.
So we can write it as like epsilon, EI, then epsilon ijk aj. What is the kth component of B cross C?
Epsilon L M B L
Epsilon K, then
L M
LM
B L C N.
BLCM.
Yeah. Yeah.
Actually, I do not want to write it as KLM. I want to write it as MN.
Okay.
So BN, BMKN. I want to write like that.
Yeah. Yeah.
So now we have EI epsilon ijk epsilon kmn aj bk cn. Sorry, BMCN. Like that.
Now we can use Levi-Civita identity.
Yes. So we want to use Levi-Civita identity, but there is a problem. We have a sum over k as well, because for Levi-Civita identity, we know like epsilon ijk, epsilon lmn. What happens? We have repeated index over here. That means we have a sum over, like set L equals to k and then sum over that thing. So use the full identity to derive that first. IL IM, IN, JL, JM, JN, KL, KM, KN. So now we set KL equals to K. Then this thing goes K, sum over, actually I'm using repeated index notation, so yeah. So then this L, this L becomes K, this L becomes K, this L becomes K.
Yeah.
Okay, so now we have delta IK multiplied by delta JM, delta KN minus delta JN, delta KM, plus delta IM, then these two things, delta JN, delta KK, minus delta JK, delta KN. Then we have then another term is delta IN, delta JK, delta KM, delta minus delta JM, delta KK. This is what we got so far.
Yeah. Okay.
Okay, so first thing, we have a sum over K. Whenever you have a sum, replace that index with the another one. So for the first term, here we have delta JM, delta, instead of K, you have IN, right? Like this K is replaced by I.
Yeah.
Then minus delta JN and delta IM. This will come in handy later. So okay, then delta IM, delta JN, but what about delta KK? How much is that?
It's just 1.
Really?
No, sorry, it's just 3.
It's 3. We saw that earlier, right? It's 3. Delta KK
Yeah.
is 3. Yeah, because we have a sum over K, right?
Yeah.
Okay, then delta IM is like that, but what about delta JK, delta KN? It's delta JN, right?
JM, delta JM.
Yeah, then what about this thing? Plus delta IN, delta JK, delta KM. What about that?
Delta JM.
Delta JM minus delta
Minus
IN, that, and
delta J.
That. What about delta KK? It's 3.
Just 3.
So now we are done almost. So can you do the algebra? Can you find the similar terms? What about the positive ones only?
Okay, sure.
First look into the not the positive one, like seek for this term, like delta IM, delta JN. Look, this term is delta IM, delta JN, right?
Yeah.
Delta IM, so it becomes 2. And do you have more here? So these 3 terms are same. So -1 plus 3 minus 1, which means we're left with delta IM, delta JN.
Yeah.
These 3 terms are gone. Then these terms. So as you can see, these are same term as well. So it gives you negative delta IN, delta JM. So it's basically the result of repeated index. So if you have delta IJK, delta KMN, then you have, so I remember like this. So forget about these two like these K indices, and you are left with IJ and MN. So it gives you delta IM delta JN. That means first one paired with the first one.